So hi everyone, it's a pleasure to be here and to be the first speaker of this conference. It's a pleasure to speak about causal decision making and the work I've been doing during the last part of my PhD, and I'm now doing at DeepMind. So all the things that I'm going to be talking about are joint work with Neil Deere, which was a colleague of mine at the Alan Turing Institute, my supervisor, my past supervisor, Theodore Molas, and Javier Gonzalez. So I'm going to be talking a bit about, mainly about static settings, and then so how can we find optimal interventions in a causal graph in static settings, and then I'll speak about how the methodology that we develop in static settings can be extended to dynamic settings. And I'm going to be starting this talk by looking at a set of systems that decompose in a set of interconnected nodes that can be thus represented by a causal graph. So you see here on the left, a causal graph representing the causal relationship between work population, soil fumigants, and the crop yield. And in this graph, nodes represent random variables, edges represent causal relationship, and dash edges represent existence of unobserved confounder. In the second graph, we represent the causal relationship between different environmental factors and the level of net ecosystem calcification. And here you also have dotted nodes, which represents variables that are observed but not manipulative, so we cannot change. And on the third graph, we have the causal relationship between different risk factors.
We're not seeing the slides progress. Are we sharing?
It's progressing for me.
Do you want
Let me just go out of the full screen mode.
That works. Yeah. Now it's progressing.
Okay, so that will have to do. Let me just. Can you see them now?
Yeah, that's good. That's good.
Okay, so I'll have to go with that. Sorry about that. So first graph, crop yield and different L1 population at different times and soil fumigants. Second graph, environmental factors or net ecosystem classification. And third graph, different risk factors, so age, BMI, cancer, but also level of statin and aspirin on process-specific antigen. So in all these systems, we can identify some common elements. So first of all, we have a causal graph. And I will refer to this as a directed acyclic graph. We have observational data from all the nodes that are non-hidden. We can run experiments either in reality or through a simulator. And the cost of each experiment depends on the number and type of nodes in which we intervene. So the goal for this talk and the methodology that I'm going to be speaking about is how to efficiently find the optimal intervention. So the intervention maximizing or minimizing a target node in a causal graph. So efficiency for us is very important because we would like to find the optimal intervention by exploiting all available sources of information. And so, for example, exploiting the observational data that we observe and limiting the number of experiments that we have to perform. So, for example, in the first graph that we looked at, we might be interested in understanding whether crop yield, we should intervene all airwork population or soil fumigants and what level we should set them to. So for all this talk, I'm going to be framing the problem in terms of structural causal model. So I thought it would be useful to give a bit of background about that. And it's going to be a very fast introduction to causal inference. So feel free later on to ask me questions. So a structural causal model is given by a four-tuple where we have exogenous background variables U, we have endogenous variables V, a set of functions that are mapping each node and exogenous factors to its children, and a probability distribution for the exogenous variable P of U. So for instance, in the causal graph that you see here, X, Y, and Z, we have an associated structural causal model on the right, where, for example, for each variable, let's say X, is a functional transformation with the function f of X of its parent C and the exogenous factor Ux, where Ux is assumed in this case to be Gaussian, to be normally distributed with mean 0 and variance sigma square X. So what we mean by doing an intervention is actually going in the system and setting the variable that we intervene on to a specific value, let's say X capital X to small x. And this is generally denoted with the do notation. So we intervene and we use the do capital X equal to small x. So on the one hand, we have an observed universe from which we can observe observational data, and we can use this observational data to estimate our joint distribution, which is observational distribution P of x, C, and y. When we intervene, we break the causal relationship of the intervened variable and its parents. So for example, in this case, capital X, and we substitute the equation for that intervened variable with a constant that is small x. And when we observe this system, we get what we call the interventional data that can be used to estimate the interventional distribution, which is written in terms of this do operator. And now these two distributions are different. And what we are interested in is the interventional distribution, because it allows us to reason about the effect of actions. So how do we do inference in this interventional distribution, where we either intervene, we collect data from the intervened system that can allow us to estimate this interventional distribution directly, or we observe, we collect observational data, and we use the do calculus to get an approximation of the interventional distribution. So for this talk, actually, it's important to know that the do calculus is a set of rules that allow us to emulate the post-intervention universe in terms of distributions that can be estimated in the observed universe. So for example, for this graph X, Y, and Z, if we want to estimate the interventional distribution for X, then we can compute this integral. And most of the time, these integrals are not available in closed form. And so we do have an approximation that is as good as, our estimation of the conditional distributions in the observed universe. So up to now, we've seen how many real systems in healthcare, in ecology, can be represented by a set of interconnected nodes. Optimizing an output in a causal graph requires performing intervention in these manipulative nodes in the graph, but the do calculus allow us to simulate experiments with observational data. So if we want to find the optimal intervention in a graph, what we need to solve is a causal global optimization problem that can be written this way, as the equation in this slide. And we're going to see the different elements together. So in a causal global optimization problem, we try to find the optimal intervention set and optimal intervention level, that are denoted by the capital X star and the small x star, that are minimizing or maximizing a quantity that is a causal effect, in this case is an average causal effect for the target node, where the expectation is computed with respect to the interventional distribution. And it's important to notice that here we are trying to explore all the possible intervention in a causal graph. So P of X denotes the power set of the manipulative node in the graph. So we want to try and intervene on 1 variable, 2 variable, 3 variable, and all the possible combination. So causal global optimization is different from global optimization. In global optimization, what we are trying to do is to find the optimal intervention level. And so we assume to be intervening on all the inputs, and we try to find the level that maximizes the target. So if we were to consider a causal graph like the one on the right, where we have as well unobserved confounder, manipulative variables, and different causation structure among the inputs, we would break the causal relationship between these inputs. And so a global optimization problem could be represented as the graph on the left. Again, differently from global optimization, in causal global optimization, we account for the causal relationship among the inputs and the outputs, and we try to find the optimal intervention level and the optimal intervention set, which is this capital X star. So one way to solve global optimization, especially when the target function is unknown, multimodal, perturbed by noise, and it's expensive to evaluate, is Bayesian optimization. So the same idea can be applied to the causal global optimization problem. So when we have the same type of setting, but we also have a causal graph that describes causal relationship between inputs and outputs, we can resort to causal Bayesian optimization. So there are 4 main ingredients to the causal Bayesian optimization algorithm. And we're going to look at them together one by one. So first of all, this power set of the manipulative nodes might be huge. And so we need to find a way to restrict the search space of the algorithm. and so limit also the type of interventions that we need to perform. We need to come up with a way to model the target function, possibly using all the data that we have, so observational data, interventional data. We need to extend an acquisition function, and in this case, we use the classic expected improvement acquisition function. So it has to be able to compare different causal effects, so this certain target function. And we also want to allow the agent to observe and intervene, depending on the structural causal model that we are dealing with. So starting from the first element, so restricting the search space, we use two notions of minimal intervention set and possibly optimal minimal intervention set that have been defined in this paper that is mentioned here, Structural Causal Bandits, Where to Intervene. And so the idea of this is to exploit some sort of invariances given the topology of the graph. So just to make this a bit more concrete, if we look at the causal graph x, z, and y here, we can notice that y is independent on x given z, and therefore the expected value of y given an intervention on both x and z is equal to the expected value of y given that we only intervene on z. So we don't want to intervene on x and z because we would pay a higher intervention cost. We're intervening on two variables instead of one, but we would be getting the same output, the output value. In some cases, depending on the structure of the structural causal model, we might be able to also determine the order among the interventional output, meaning we might be able, for example, in this case, to determine whether the expected value for an intervention on X is always smaller or equal than the expected value for an intervention on another variable. And if this is the case, then we can obviously exclude this set from the search space. So once we have restricted the search space, we need to find a way to construct a surrogate model for these causal effects. And we do that by noticing that we use Gaussian processes, but we construct the mean function and the kernel function of the Gaussian process in a way that allow us to exploit the available observational data, so the data that we get from the non-intervened system. Specifically, these expressions that are written in blue corresponds to, for the mean function, the estimated average causal effects that we can estimate with the do calculus and observational data, while the sigma xs corresponds to the standard deviation of the causal effects, also computed with the do calculus, and so approximated with observational data. So the idea is that we use an RBF kernel for the kernel, but we also inflate the variance terms to account for the uncertainty that we have on the mean function that is, again, an approximation. And we do that, so we construct this type of surrogate models for all causal effects, so the causal effects corresponding to each intervention set that we want to explore. So for instance, if we look again at our example x, z, and y, we've seen how we need to explore only x and z individually. And on the right, you see this one-dimensional function that are the causal effects for this causal model of an intervention on x and an intervention on z. So the idea is that we want to compare the minimum of these two functions, so that are denoted by the dotted line here for x and z. And we want to find the one that corresponds, that associated to z, which corresponds to the global minimum. And so if we look at, for both functions, we construct the surrogate model as we discussed now. And I'm going to show you how the surrogate model looks for one function, specifically the causal effects for x. So on the top row here, you see the causal, this function with the causal GP prior construction. And on the bottom row, you see the corresponding GP construction where the mean function is set to 0, and we use an RBF kernel. In the dotted row nodes, the dotted red points corresponds to interventional data point, where the green crosses corresponds to observational data. And so it's just to show you where the observational data are observed in the input space. And so the idea is that by using this observational data, we can come up with a model that captures the true behavior of the function, even in areas where we don't have interventional data. Say, for example, between -2 and 0 in the top row. Obviously, where we don't have observational data, so for example, for inputs lower than -4, the function would only go back to the prior, and it will not benefit from having this prior construction. However, it's still much better than what we would get by using a zero mean RBF kernel. Indeed, you know, if you see from the bottom row how the posterior mean function, which is the blue line, would just pass through the data, but it would not capture the behavior of the function in areas where it doesn't have interventional data. So once we have this surrogate model construction, we need an acquisition function. In this case, we use an expected improvement acquisition function that allow us to decide which interventions to collect next. And the idea now is to compute the expected improvement for every function, for every target causal effect, with respect to the optimal observed so far. So this is y star in the first equation on the left. And we rescale it by the cost of an intervention. And this is to account for the fact that if we have two interventions giving us the same type of expected value, we still want to explore the one that has a lower cost of intervention. So you can see for the same example, x, z, and y, the two acquisition function computed for x. This is the red line, and for z, the black line. And you see the dotted corresponding, so the dots in red and the dot in black, capturing the maximum of the acquisition function for both x and z. What we want to find, to identify, we want to, you know, the intervention that we want to collect next is the one corresponding to the blue dashed line. So we want to intervene on x around minus 3. Now, the last element of this causal Bayesian optimization algorithm is this epsilon greedy sort of criteria that allow us at every iteration in the Bayesian optimization loop to decide whether to observe or to intervene. We decide to observe whether to observe or to intervene according to this epsilon, which is determined by this formula here. I'm just going to give you an intuition. The idea is that we want to decide whether to observe or to intervene based on how much of the input space that we are interested in exploring is covered by the observational data. So you see here this graph where you have the outer black line that corresponds to the interventional domain, which is fixed by the user. And in red, you see the convex hull of the observational data. So if you're interested in learning about an intervention around, let's say, 0, 0, you see that that part of the input space is pretty much covered by the observational data. So that means that you can get a pretty good estimation of what the causal effects looks like in that specific intervention value. If instead you're interested in understanding the minimum and the optimal intervention for an intervention around -4, 5, that's probably not going to be accurately inferred by using observational data. So if our interventional domain is much larger than the convex hull of the observational data, we want to intervene more. Vice versa, if the observational data are capturing, the interventional domain that we are interested in, then we want to observe more. So overall, putting all of these elements together, we get to our causal Bayesian optimization algorithm. So you'll still have a Bayesian optimization loop. So you're going to collect interventions sequentially. At every step, you're going to decide whether to observe or to intervene. If you observe, you collect observational data, so you can update the prior distributions for the causal effects. If you instead intervene, you can update your posterior distribution for the intervention that you have performed. We are going to look very quickly at two experimental results. On the left, you see the causal graph that is associated to the convergence result on the right. So causal graph, and on the right, you see how fast the algorithm, so both causal Bayesian optimization and Bayesian optimization, are converging to the optimal solution. The blue lines give the result for Bayesian optimization. Green and black lines give result for causal Bayesian optimization. Dashed lines are associated to a standard zero mean RBF kernel, while the solid lines are associated with the GP construction that I spoke about in the slides. And the first thing to notice is that Bayesian optimization is converging to a value that is different from the one to which causal Bayesian optimization is converging. And this is because Bayesian optimization breaks this causal relationship between the variables. So it blocks the the causal effect propagation in the graph. On the other hand, Causal Bayesian optimization instead finds the optimal, which is an intervention only on some nodes, B and D. And it does allow this propagation of causal effects in the graph, and so achieves value of the target node that are not achievable by standard Bayesian optimization, and has expected using observational data and the prior construction we spoke about allow us to converge faster than when using surrogate models with a zero mean RBF kernel. And we use the same type of algorithm, for example, to select the optimal type of drug dosage, starting in aspirin, in order to minimize the level of process-specific antigen. And surprisingly, we found the optimal interventions to be maximum level of statin, lowest level of aspirin, which is consistent with the domain knowledge. So there are several, take-home messages for that. I'm going to try to summarize it for you. So standard Bayesian optimization ignores causal assumption. And so in order to find optimal intervention in a causal graph, we need to solve a causal global optimization problem, which can be solved with Causal Bayesian optimization. Causal Bayesian optimization avoids exploring all the, explore all possible intervention in a causal graph. It constructs surrogate model using observation and interventional data, solving therefore the exploration-exploitation trade-off within a single function, but also the observation intervention trade-off thanks to the epsilon greedy policy. Now we have different, limitations for CBO, for Causal Bayesian optimization. So first of all, you might have noticed that we have a lot of surrogate models that are associated to each causal effects in the graph that might be potentially huge. And we also don't transfer interventional information across GP. So every time that we intervene on a set, we only update the Gaussian process that is relevant to that intervention. So a way to avoid this is to construct a multitask model that can be used as a surrogate model in the same type of algorithm. And this is being developing the DAG-GP framework that you can find, the relevant paper, for which you can find the relevant paper online. We also have addressed the problem of assuming a non-causal graph by extending the acquisition function to account for uncertainty in the causal structure together with uncertainty regarding the optimal intervention. And this is what led to the causal entropy optimization algorithm. So today I'm just going to give you an introduction to instead dynamic Causal Bayesian optimization. So you've noticed how in CBO we do not account for time, and we do not account for the fact that causal relationship might change over time, but in terms of the causal graph might change, but also the functional relationship linking different variables. And you can see the results of this dynamic Causal Bayesian optimization in this paper that is indeed called Dynamic Causal Bayesian Optimization. So the idea is that if we get our same graph X and Z and we unfold it in time, we get to the causal graph on the right. And the causal effects for an intervention on X at different time steps are different. So for instance, if you look at the, at the causal effects at time 0, 1, and 2, you see how the optimal intervention, which is denoted by this red cross, changes over time. It changes in terms of variables. So at time 0, the optimal is an intervention on Z, time 1 is an intervention on X, but also in level. So at time 1 intervention on the optimal intervention is at X around, let's say, 0.5, and then at time equal 2 is at X at level 1. And so what we want to solve in this case is a dynamic Causal Bayesian optimization problem that is very similar to the Causal Bayesian optimization, the Causal Global Optimization problem, with a difference that the target function has this additional term that tells you that you should account for the previously implemented intervention in the system when deciding what to do. So the idea is that now, because we have collected interventional data at previous time step, we want to reuse as much as possible these interventions and do not throw away all that we have learned in the past. And we want to use these recursion, so we want to link causal effects across time step and use that to construct a surrogate model. So for example, just to make the problem a bit clearer, at the first time step, you're solving still a causal global optimization problem because we don't have intervention implemented in the past. Suppose now that we have found the optimal intervention to be on Z levels as 0, then we set this value, we move to the next step, And the optimization that we need to perform needs to account for the fact that we have implemented the intervention in the previous time step. And so the graph at time 0 is mutilated to reflect the optimal intervention found. And this is, going on in time. So we're going to do that. So we're going to try to derive this recursion across time steps under 3 main assumptions. So first of all, that we have invariance of the causal structure. So the graph at every time step is the same. We have an additivity, meaning that the functional relationship for y can be split in a part that depends on its variance and a part that depends on other variables. And we have no unobserved confounder. Notice that if we look at this assumption in the causal graph that we've seen so far, we assume, invariance of causal structure, but that means that the orientation of the edges at every time step is the same. However, the time transition might be different. So we might have different parents for Z1 and Z2 because of the time causal relationship. The functional relationship instead of additive means that, for example, y1 is a function of y0 and another term that is a function of z1 that is the other parents, but these functions are non-linear. They are actually modeled with Gaussian process. So these allow us to capture a lot of different causal effects configuration. So it turns out that actually the causal effect at every time step is determined by two elements, 2 components. So the first component is given by the optimal values of the target propagated through y1, propagated in time. And another element that is determined by the other parents of y1, for example, and previously implemented interventions. So if we make this a bit more concrete, because it might be, the notation is quite cumbersome. If you look at the example 1, you see how at y1, suppose that we want to evaluate an intervention on z1, y1 is determined by the previously optimal intervention for y0 propagated through the edge that is highlighted in red, and the intervention level for z1 propagated through the edge that is highlighted in orange. If we look, for example, instead at an intervention on x1, the causal effects, again, for y1 is determined by the previously found optimal level for y0 propagated through the edge that is highlighted in red, and then the level of intervention for x1 propagated again through these 2 edges highlighted in orange, but also considering the effect of previously implemented interventions, so z0 on z1. So exploiting this recursion, we can then use, we can define the mean function and the variance function as we were doing in CBO, but including this recursion. So again, the mean function will be determined by the approximated average causal effect with observational data plus a term that depends on the found optimal interventional level at previous time step. And so this recursion allows us to integrate observational data, interventional data at the current time step, as in CBO, but also interventional data collected at previous time step. So it responds to our need to be efficient in selecting interventions. So again, the algorithm will be very similar to Causal Bayesian optimization. We'll still have a Bayesian optimization loop, and we're also going to have an outer loop across time. So at every time step, we're going to initialize the dynamic causal GP model. We're going to collect data. We're going to find the optimal, then move to the next step and use whatever we've learned before to initialize our dynamic causal GP model. So if we were to look at the high level at where all these algorithms fit, we might consider, 2 different dimensions of these optimization algorithm. So we have the temporal dimension, we have the causal dimension. CBO allow us to capture the causal dimension, but it doesn't capture the temporal dimension. Bayesian optimization does not capture causal dimension nor temporal dimension, so it breaks every causal relationship and does not consider time. In the literature, we also have an algorithm that is called adaptive Bayesian optimization that considers time in the Y, but not in the inputs. And then dynamic Bayesian optimization, causal Bayesian optimization that consider both aspects. So it does consider the full causal graph that we've seen so far. So going back again now to the X, Z, and Y experiment, you see how in the second row, we have a surrogate model that is shifted downwards. So this is just a linear shift, just to show how the algorithm behaves. And using this surrogate model allow us to, get the shift, infer the shift correctly, and so find the optimum faster. Also, identifying changes in the optimal intervention set, optimal intervention level. And so if we look at the convergence, the CBO converges the same as CBO has expected for the first time step, but then finds the optimal intervention faster at following time steps. And we've tried, these algorithms in multiple settings where, for example, we have multivariate interventions that are optimal, where we have no causal relationship across the nodes, across the inputs, where we have non-stationary, graph that changes over time. For example, in this non-stationary case, we have Y2 that has parents Z1 and Z2, but Y1 only has Z1, so there's a change where the functional relationship are changing, so on and so forth. And we found the CBO to be a good choice in terms of and leading to the consistently outperforming all the other methods across different examples. Obviously, if you have no causal relationship across the inputs, then the performance, the convergence speed is worsened, and in that case, CBO and BO are performing better. And when you have multiple, multivariate interventions that are optimal, then the convergence speed is also worsened. I'd just like to finish by saying that this CBO does not look forward in time. It's just one step ahead sort of method. So it just selects the optimal intervention, given that we find the optimal at the previous time step. And so we've repeated the experiments by limiting the number of interventions that we can perform at every time step. So it has to see the effect of not being able to identify the optimal before moving forward. And obviously, there is, nothing that we can say about, average sort of regret or non-myopic sort of regret. Right, so take-home messages from this last part. Identifying optimal intervention at every time step requires solving a dynamic causal global optimization problem that can be solved with the DCBO algorithm, which proposed use surrogate models integrating all available data across time step and identifying intervention faster than CBO in dynamic settings. Now, there are multiple future research directions, just to mention a few. Again, I mentioned in the last slides, non-myopic acquisition function could be explored. The target could be changed to consider a conditional average treatment effect for personalized medicine, for example. The causal Bayesian optimization algorithm could be, adapted to deal with discrete outputs and more general non-Gaussian likelihood. And finally, there's still the question of how to address the causal discovery and causal optimization jointly, potentially. I'd like to conclude thanking you. And if you want more information about what I've talked about today, you can find it in these two papers. Thank you.